Hello, my name is Harry Chen. I'm the newest board member on CNCM, and as such, I will be covering today's lecture. This lecture is about Jensens Inequality, as you can see, and it is not my lecture. It was written by Paul Hamrick, so thanks to him for providing us this lecture. Let's proceed. What is Jensens Inequality? Well, Jensens Inequality states that for a convex function f that maps x values in the interval u to v to real numbers, where we also have some, just numbers a that are inside that interval. We have that the sum of f of a is greater than or equal to n times f of the sum of a over n. So if the function is concave instead of convex, it'll actually be flipped. It'll, instead of being a greater than or equal to sign, it'll be less than or equal to sign. So yeah, those are the two cases. Now, typically, you'll actually not see Jensens inequality stated like this. Typically, it won't actually have the n over here. It'll have the n over here on the left side. This kind of makes it more symmetrical, but in practical usages, it's not really as effective. Typically, you're going to have to move the n to the right side anyway. So this formula is a little bit confusing. I get confused by these formulas all the time, so let's come up with a concrete example. So let's say that n is equal to 3, which is to say that we only have 3 a values. This means that f of a, 1, plus f of a 2, plus f of a 3, all over 3 is greater than or equal to f of a1 plus a2 plus a3 all over 3, only if f is convex. Of course, the reverse would be true if f was concave, in which this would be a less than or equal to sign instead. So that's generally how you would use this. Use the Jensens inequality. Now, we mentioned that the function is either convex or concave, but what does that actually mean? So, if you take in calculus, then the definition really is that the second derivative of f is positive if f is concave, and the reverse. And the opposite is true when it's concave. When it's concave, the second derivative of f is negative. It's less than 0. So those are the two criteria. Those are when it's convex and concave. If it's equal to 0, that's a little bit of a fuzzy area, but luckily, a function can only be equal to 0 in an interval if it's linear. So you almost definitely will never have to worry about that. So if you don't know calculus, you don't know what the second derivative is, two things. Number one, CNCM will be releasing a calculus lecture at some point in the future. And so, of course, we're going to cover derivatives. And so once we learn about that, you can use calculus. That's one application of calculus, certainly. And number two, you can actually, if you don't know how to take a derivative, you can actually kind of look at the graph. So, okay, so yeah, some of the common functions that are convex are like x squared, x cubed, e to the x, as you can see down here, and then concave is kind of the opposite. So the nth root of x is going to be concave. Same thing with the logarithm of x. It's going to be concave. So if we look at these graphs, let's label these concave, convex. We have something like x squared, right? This is x squared. And then we also have like e to the x, kind of looks like this. And these are some examples of convex functions. And concave, instead it looks kind of like this, or like this. So you can see there's some visual similarities here. So convex functions open upward. They're like a cup. They open upwards like a parabola. Same thing here. This doesn't. The left side here doesn't really like open upward, but it kind of goes to the side. But it's the same concept. Concave functions are the opposite. They open downward like this. Now, the official definition for opening up, quote unquote, is that if you pick any 2 points on a convex function, so we'll pick this point and this point. If we draw a line between them, if we draw the secant line between them, we'll notice that the secant line is always above the function itself. Like, it's always above it. We can contrast this with a concave function. If we choose any 2 points on the concave function and draw a line through it, it's going to be always lower than the function. And so that's how you visually determine whether a function is concave or convex. Or, if, of course you could just type in your calculator and see if it's positive, but either way works. So typically, you can't just look at the function and state that in a proof that it is concave because it looks like it. You have to either take the derivative twice, or it has to be like a famously concave or convex function. Such examples are like, as we mentioned, the nth root of x is going to be concave. X to the a, any power is going to be convex, as long as x is positive. Logarithms are going to be concave, and then exponentials are going to be convex. So, yep, that's how concavity and convexity work. That's all the theory for Jensens, really. Now we can use it. So, we're going to start by using Jensens to prove QMAM. Okay, so QMAM goes as follows. When we have p is greater than 1, so already we can see that it's going to be something like a power. And we have positive reals x1, x2, all the way up to xn. We have that the sum of x over n is less than or equal to the sum of x to the pth power all over n to the 1 over pth power. Visually, this looks a lot like Jensens inequality already, because we have on over here we have x to the p being summed up and then all divided over n, and over here we don't really. It's kind of similar. We still have x being summed up here, so that's a good hint that we may want to use Jensens. So in fact, right now this form isn't actually very applicable to Jensens, but if we raise both sides to the power of p, we get that this is actually going to be equal to this. The sum of x over n to the pth power is less than or equal to x, the sum of x to the p over n. And so now we can kind of apply Jensens directly. If we let f of x equal x to the pth power, we know that this is going to be convex. And so it's pretty easy to see that this inequality holds true. Yeah, let's move on. So we can apply this to computational things as well. So, for instance, the Purple Comet competition is an online competition. We have that if A, B, and C are non-negative real numbers satisfying A plus B plus C is equal to 400, find the maximum possible value of all of this. So, I'm going to go to the blank slide. We have square root of 2A plus B, the square root of 2B plus C, plus the square root of 2c plus a. So when we look at this, we see that there's really only one function that really stands out at this, and that's kind of the square roots on each of these terms. And so that clues us in that we might want to let f of x equal square root of x. Oops. And so f of x equal to square root of x. We know that the square root of x is going to be a concave function that looks like this. Plus, we had the rules before. And so we can say that this, I just say convex or concave. It's a concave function. But anyway, because of that, we can say that this is going to be less than or equal to the 3, since there are 3 terms, square roots of 3a plus 3b plus 3c, that's a b over 3. Where do we get this from? Well, 2a plus b plus 2b plus c plus 2c plus a is equal to 3a plus 3b plus 3c. And then we divide that by 3, and so this is going to be equal to 3 times the square root of 400, which we know is going to be equal to 60. Now, don't forget that we have to show that it's possible to achieve this. In Jensens, equality is achieved when x1 or when a1 is equal to a2 is equal to ... is equal to a, and basically when everything is equal. And so we just have to set 2a plus b equal to 2b plus c equal to 2c plus a. And trivially, this means that a is equal to b is equal to c. Is equal to 400 over 3. And we can kind of just test that and see that it is indeed equal to 60. And so 60 is the answer. So that was a relatively straightforward application of Jensens. Now we can get into a little bit more complex of things. So this is a MOP question, so we know it's going to be hard. Yeah, so for positive real numbers a, b, c with a plus b plus c is equal to 3, prove that the cyclic sum of the square root of a cubed plus b cubed over a plus b plus 9 cube roots of a, b, c is less than or equal to 12. Firstly, to understand what the cyclic sum is, cyclic sum basically just means that it's we substitute a comma b in, and then we substitute b comma c in, and then we substitute c comma a in. So really, this is equal to the square root of a cubed plus b cubed over a plus b plus the square root of b cubed plus c cubed over b plus c plus the square root of c cubed plus a cubed over c plus a plus 9 cube roots of a, b, c is less than or equal to 12. So now what we can do is, let's go over here. We know that a cubed plus b cubed over a plus b is equal to a squared minus ab plus b squared. Yeah, we can. You know this mainly because of the sum of cubes formula, or just you can just straight up divide it. So now, if we really want to, so now we gotta really figure out how to deal with the cube root of ABC situation, because this is kind of hard to really do when we have cube root of ABC, or 9 cube roots of ABC. And so we can use AMGM. By AMGM, we know that this is going to be less than or equal to the square root of AB plus the square root. I think there's a 3 term here. Is less than or equal to 3 times the square root of AB plus square root of BC plus square root of CA, I believe. Yeah. Right, and so we know that this the whole thing here, I'll just call it like question mark or whatever, is less than or equal to cyclic sum of a squared minus ab plus b squared plus 3 square root of ab plus square root of bc plus square root of ca. Okay, cool. So now what we're going to do is, we notice there's a lot of symmetry, because really this thing, all of this here can be written as 3 times the cyclic sum of square root of AB. And so again, we can kind of just combine these together, set these two cyclic sums together to get 3 square roots of AB. It's the cyclic sum of all of this. Yeah. Okay. So, now what we do next is, oh wait, I forgot to put a square root around these. It's my fault. So, if we look at this, we see that there's a lot of square rooting going on. So, let's let f of x equal square root of x. We know that, again, that this is going to be a concave function. So we know that, so at least for the square root of a squared minus ab plus b squared, plus 3 square roots of ab is going to be, since the concave is going to be less than or equal to 4 square roots of a squared plus 2ab plus b squared all over 4. So how do we get from here to here? Well, notice that 3 square roots of a squared of 3 square roots of ab is equal to square root of ab plus square root of ab plus another square root of ab. And so really we can, this is kind of 4, if you imagine this kind of all like 4 terms, which is why we have a 4 here and a 4 here. And yeah, and so inside this thing here we just kind of added a squared minus ab plus b squared plus ab plus another ab to get this. And we can factor that together to get, notice that a squared plus 2ab plus b squared is equal to, open parentheses, a plus b, close parentheses, all squared. And so really this is all going to be equal to, well, let me write this a little bit more cleanly. And so really we know that this is going to be equal to, when we're all done with it, it's going to be equal to 2a plus b. And so we have that this whole cyclic sum here is really just going to be less than or equal to 2a plus b plus 2b plus c plus 2c plus a. Whoops. And we know this because it doesn't matter what a and b are in this situation. It could be b, c, or ca. It's going to come up with the same result. And so this means that since we have this a plus b plus c is equal to 3 equality here, that this is going to be equal to, I think 12? Yeah, 12. Yeah, 12. So, yeah, and then we can manually check that that this holds true throughout all of this. Yeah, I'm not going to go over that. You can check that for yourself. Okay, and then this this is our no, this is not our final slide, but this is our final problem that we're going to do, and this is probably going to be the hardest of all of these. So it's an Elmo SL 2019 A1 question. Let ABC be positive reals such that 1 over A plus 1 over B plus 1 over C is equal to 1. Show that A to the A times BC plus B to the B times CA plus C to the C plus 8 times AB is greater than or equal to 27 BC plus 27 CA plus 27 AB. Right. So this is kind of a tricky one. Early on, we see that if we divide both sides by ABC, this actually makes it very pretty, because then we have A to the A minus 1 plus B to the B minus 1 plus C to the C minus 1 is greater than or equal to just 27, because after we divide everything by ABC, we get 27 over A plus 27 over B plus 27 over C, and so we can use the equality case over here. So cool, we just have to prove this now. So this should be a very obvious function that we see right here, because all three of these terms each have it, and so that is, let's let f of x equal x to the x minus 1. This is a very weird function to take the derivative of, but I'm going to try to ignore derivatives right now. And so if we kind of just graph this, because this isn't really a function we've seen much before, it kind of looks like this. Notice how it's a cup shape, and so we can conclude that this is a convex function. To get a to make this rigorous, you're actually going to take the derivative. All of those steps can be found over here, these are all the derivative steps, and you can take that for yourself, or if you know calculus, feel free to read that. So, using Jensens, since we know this is convex, we know that this, or rather a to the a minus 1 plus b to the b minus 1, c to the c minus 1, is greater than or equal to 3 times a plus b plus c over 3 to the, I was kind of in the way, a plus b plus c over 3 minus 1. This is one heck of a thing. This one heck of a, just kind of insane, but, so now we have to find what a plus b plus c over 3 is. To do that, we'll use Cauchy-Schwarz. We will be releasing a lecture on Cauchy-Schwarz in the future as well, so stay tuned for that. But Cauchy-Schwarz basically states that, well, it allows us to conclude that a plus b plus c times 1 over a plus 1 over b plus 1 over c is, well, this is going to be greater than or equal to, I think it's just 3. Or, I'm sorry, it's 3 squared. There we go. Yeah. And so this, of course, is going to be equal to 9. That means that when we and so since this is equal to 1, we get that a plus b plus c is, in conclusion, equal to 9. Or greater than equal to 9, but same difference. So let's continue. Yeah, so let's continue. So this means all of this is greater than or equal to 3 times 3 to the 3 squared, which is equal to just 27, as desired. Of course, we can check this. Set a equal to b is equal to c. Is equal to, I think, like 3 is what it is. Yeah, 3. And then we'll see that the entire thing carries through and all the equality is conserved. The final thing we're going to discuss is the Jensens Inequality, is the tangent line trick. So this basically states this: f of x is greater than or equal to f of a plus f prime of a times x minus a, where where f is a convex function. So so really what this is saying is that if we I'll write it down here, f of x is greater than or equal to f of a plus f prime of a times x minus a. If we have a convex function like this, then f of x, so let this be x comma f of x, is always going to be greater than some line like this. So we'll let this be a comma f of a. And so this is the tangent line. It's the line that it's a straight line that intersects this function at really only one point, and that is this point right here. We'll see that this is always going to be greater than it, no matter what x we choose, or no matter what x or a we choose. It's going to be greater than it no matter what. Even if x is over here, it's still greater than it. As you can see, yeah. And of course, it's going to be equal when x is equal to a, which is this point. So I'm not going to go over the proof very in depth. The proof is really over here. If you have a good grasp of calculus, you should be able to at least go see up to this step over here. So I'm going to explain this step. So to prove how we get from here to here, all we really have to show is that the integral from a to x of f prime of u, du, is greater than or equal to the integral from a to x of f prime of a du. Note that f prime of a is a constant. It's just a number. So when we integrate with respect to du, it just turns kind of into a rectangle. And so we can kind of prove this graphically. Yeah, we can kind of just prove this graphically. So let's say we have another curve like this. That's not a really good curve. Another curve like this. So it's we know that actually I don't want to explain it like that. We know that the derivative of f prime of x is going to be equal to f double prime of x. So that's to say that f double prime of x is really the slope of f prime of x. So since we know that this is going to be greater than 0, since it's convex, we can see that we know that f prime of x is going to be increasing. It's an increasing function. So if we start at if we graph f prime, we have something like this, where this point is x equals a. If we take this area over here, we can interpret it as the literal area under the curve. And so this is just going to be this part here. Actually, color this. So this is going to be this area. Whereas this part here is going to be this area. And so obviously the blue area is going to be greater. And so you can kind of follow the rest of the steps over here to finish the proof. And that concludes our lecture. We have 2 problems at the end here that you can kind of try using Jensens if you want. They're good practice. And of course, we're going to have some Jensens problem of the days as well this week. So, yeah, have fun using Jensens. Make sure to subscribe to our YouTube channel if you want more content like this, and join our Discord because we have practice for Jensens if nothing else. So, yeah, thank you for watching.